I'm glad to introduce DaoZhou Gao, who from Shanghai Normal University. He will talk about relative contribution of multiple transmission routes for Zika virus disease. So please, it's time to start.
Okay, good. Thank you. So first, good morning or good afternoon, everyone. So first, I would like to thank Professor Magar for the invitation. So today, I'm not going to talk about the ongoing COVID-19 pandemic, but the 2015 to 16 Zika outbreak. Okay, so as you can see, so my talk is divided into 4 parts. So first, in the first part, I will give a brief introduction to Zika virus disease. And then in part 2 and 3, I will present a Zika epidemic model and a Zika endemic model, respectively. And I will give a short discussion and ender. Okay, so first, background. So Zika virus disease is also called Zika fever or Zika. It's a mosquito-borne disease caused by Zika virus. So about 20% of Zika infections are symptomatic, and the common symptoms include like mild fever, skin rash, red eyes, or joint pain lasting 2 to 7 days. And besides mosquito-borne transmission, the disease can also transmitted through blood transfusion, mother to children, or sexual contact and other ways. Okay, so far there's no specific treatment or vaccine for Zika. Okay, so recently 2 serious outcomes of Zika infections have been identified. So one is a microsymphonia in newborns. So if for this case, so like microsymphonia means like the children, newborns like with small head, right? They may have like both defects. Okay, so the other is Guillain-Barré syndrome. So this can cause muscle weakness and sometimes paralysis. So and the virus was first isolated from a monkey in Zika forest of Uganda in 1947. So that's the reason why it is called Zika virus. Okay, so and there were only like a few. There are only sporadic reported human cases for a long time, in a long time. The first documented Zika virus outbreak occurred on Yap Island in 2007. And then in 2013, a serious Zika virus outbreak was reported in French Polynesia. And then the virus was rapidly spread across Oceania. Okay, so since April 2015, so a large outbreak of Zika virus occurred in Brazil and then spread to over 60 countries in South America, Central America, the Caribbean, and Mexico. And it caused millions of cases of Zika virus and thousands of cases of microsymphonia. And the WHO, the World Health Organization, declared that the Zika epidemic constituted a public health emergency of international concern on February 1st, 2016. And the US CDC mourned the response to Zika to the highest level of activation on February 3rd, 2016. So the 2015 to 16 Zika epidemic caught my attention in January 2016. At that time, I was thinking about what can I do? What could I do as a modeler in response to the epidemic? And I did a literature search, but there were only like very few modeling works. So to build a new model, I wonder what makes Zika virus disease different from other mosquito-borne disease. Okay, so then a Chinese popular science article inspired me. So this title translated into English is New Scientific Discovery Induced by Sexual Intercourse. It tells a very interesting story on how sexual transmission of Zika was discovered. And it is based on a paper published on emerging infectious disease in 2011. So if you have interest, you can read this. You can also read this English article on Science. Okay, so besides the emerging infectious disease paper, there were also a few weak evidence supporting the sexual transmission of Zika virus as of January 2016. So the virus was detected in urine, saliva, and semen. And a mosquito-borne disease can also sexually transmitted. That making Zika unique, right? So based on those limited information, so I want to propose a Zika model that incorporating both sexual transmission and mosquito-borne transmission. And then I want to estimate the basic reduction number of Zika and evaluate the percentage of contribution of sexual transmission to Zika. Okay, and also I want to know the impact of sexual transmission on the prevention and control of Zika. Okay, so during my study, new evidence of sexual transmission of Zika virus appeared. So on February 2nd, the first sexually transmitted Zika virus case of the 2015 to 16 Zika outbreak was reported in Dallas County. And later on, so more sexually transmitted Zika virus cases of Zika virus were reported in more countries. And the WHO said sexual transmission of the Zika virus is more common than previously thought on March 8th, 2016. So I was very happy because we were on the right track, right? So that means like sexual transmission is very important, and we should consider sexual transmission in modeling the transmission of Zika virus disease. Right? Okay, so here is the model flow diagram we developed. So here the basic model structure for humans is SEIR. And the model structure for mosquitoes is SEI. So here the human population is divided into susceptible and exposed and symptomatically infected humans and the convalescent, and then the asymptomatic infected humans and recovered. So here we divided the symptomatic infected human into two, the symptomatic infected humans and the convalescent humans. That's because in this stage, there's no virus in human blood, but there's still virus maybe in other body fluid like semen, right? So for people during infected people during their convalescent stage, right? In this stage, they can sexually transmit the disease to their partners. But they cannot transmit the virus to mosquitoes because mosquitoes biting humans, they take feed blood, right? And susceptible humans can become infected by the bites of infectious mosquitoes or by sexual contact with exposed symptomatic infected or convalescent humans. And susceptible mosquitoes get infected by biting exposed or symptomatic infected humans. Okay. So then we can write down the model equations, and the first equations are for humans, and the remaining three equations are for mosquitoes. And here, this term is for the mosquito-borne transmission, represents the term for mosquito-borne transmission in humans, and this is for the sexual transmission in humans, right? And then this term is also for the mosquito-borne transmission in mosquitoes. And the parameter theta, so the parameter theta is the proportion of symptomatic infection in humans. Okay, and in this model, you can see that the vital dynamics for humans are ignored, right? Because we do not consider the human births and deaths. So that means this model is an epidemic model. Okay, and then so here is are the descriptions and ranges for model parameters. Okay, and then based on the model, we define the basic reproduction number. So this basic number R naught is is a mix of the basic reproduction numbers associated to sexual transmission RHH, and the RHV is associated to the reproduction number of the mosquito-borne transmission, right? That means like if there's no sexual transmission, they are not equals RHV. If there's no mosquito-borne transmission, they are not equals RHH, right? And then we fit the model to reported case data in Brazil, Colombia, and El Salvador. And we find that the reproduction number for Zika is about 2, and the percentage of contribution by sexual transmission in R naught is about 3%. And in addition, we perform a sensitivity analysis, and the sensitivity analysis shows that R naught is most sensitive to the mosquito biting rate and the mosquito mortality rate. Okay, and so based on this result, we find that the relative contribution of sexual transmission to Zika virus is small, and reducing mosquito bites and killing mosquitoes is the most effective strategy against the Zika. Okay, and since this work was later published in scientific reports in June 2016, and it is the first modeling study with both like sexual transmission and the mosquito-borne transmission for Zika virus. So, and it received massive media coverage and cited by the European CDC and the top journals. And it also included as a subsection in the monograph written by professors Fred Brower, Carlos Castillo Chaves, and Zhilan Feng in their book. Okay, and so this is the first part. So okay, so later on, since 2016, many Zika model with sexual transmission have been proposed and analyzed. Since my time is limited, I won't go through the details. Go into the details. Okay, so there are also quite a few Zika models without sexual transmission. Okay, so in the first part, I just presented the model I presented ignores human births and deaths. So it is an epidemic model that is suitable for studying like a disease outbreak over a short time period. But however, when like Zika became endemic in a region, we are interested in the long-term dynamics, and so then it is necessary to incorporate birth and death processes. So in part 3, I will take human birth and death into consideration and propose an endemic model. Okay, so recent studies find that Zika virus can also transmitted vertically in mosquitoes. So we aim to develop a mathematically tractable Zika endemic model with 3 transmission routes. So that is the vector-borne transmission between humans and the mosquitoes, and the sexual transmission with humans, and then the vertical transmission within mosquitoes. Okay, so in fact, there was already a paper published in Infectious Disease Modeling in 2018. So in this paper, the paper also considered like these 3 transmission routes, but the model is very complicated. So they only doing like some numerical simulations, do not perform like a rigorous mathematical analysis. So here we want to develop a mathematically tractable model. Okay, so then based on the model, we want to study the percentage of contributions of each transmission pathway. on the basic reproduction number, and also the short and long-term host infections. And then we want to evaluate the impact of secondary transmission on the prevention and control of Zika. So here is the model. Here is the model flow diagram, and you can see the model structure for humans is SIR, and the model structure for mosquitoes is SI. And here you can see, so the susceptible humans can become infected by like sexual transmission or by the vector-borne transmission. Okay, and the mosquitoes can become infected only by the mosquito-borne transmission, right? Mosquito-borne transmission or by the vertical transmission. So here the theta, the parameter theta is the proportion of congenital infections in the offspring of infected female mosquitoes. So this is for the vertical transmission. Okay. So in this, so then we can write down the model equations. So here are the model equations, and the parameter mu h is the human birth and death rates. So now you can see this model is an endemic model, right? Because we consider both the birth and death for humans and mosquitoes. And the model actually is a generalization of the Benedict's model. So the Benedict's model, and by incorporating sexual transmission in humans and vertical transmission in mosquitoes. Okay. And the global dynamics of the Benedict's model was studied in these two papers, and the dynamics are completely determined by the basic reproduction number. Okay. So here are the descriptions and ranges of model parameters. Okay. And you can see the parameter theta, right? Theta is the proportion of congenital infections in the offspring of infected female mosquitoes. So this number is very small. That's for the vertical transmission. And so since the birth and death rates of of host and vectors are the same, so then the population size of host and the vectors are constant. So then the model system can be reduced to a three-dimensional system. So now we only need to study this three-dimensional system if we want to study the disease dynamics. Okay, and it's easy to show that the model system is well posed, and omega is a positively invariant for this model system. Okay, so we only need to consider the model system in omega, right? So that's very simple. Okay. So then we can use in the next generation matrix method to define the basic reproduction number R0. So R0 now it is a function of the RHH and the RHH and RVV and RHV. So RHH is associated to the sexual transmission. RVV is associated to vertical transmission, and RHV is related to mosquito-borne transmission. Okay, so this is the R0, right? But you can see the R0 is somewhat complicated. Okay, so then we can use by Lyapunov function method. By Lyapunov function, we construct a Lyapunov function, and we can use the Lyapunov function method to showing that the global dynamics are completely determined by the basic reproduction number R0. So that means if R0 less than or equal to 1, then the disease-free equilibrium is globally asymptotically stable. And if R0 is greater than 1, then there exists a unique endemic equilibrium E star, which is globally asymptotically stable. Okay, so the disease dynamics are very simple. Okay, and so then we want to study the relative contribution of each transmission route to the reproduction number. So here you can see the previous. Let's go back to the previous the R0. So here you can see the R0 is a mix of RHH, RVV, and RHV. It's very difficult to figure out the contribution of each transmission route, right? From this R0. Okay, so then we try to define a new R0. So we redefine the reproduction number by considering only a new host infections as new infection, and the new vector infection as transition, new vector infection as transition. So then you can see that. So here we have new like incidence matrix and transition matrix. But here we move into these two terms, the ACM over H, right, and the mu V times theta. This previously these two terms are in the F matrix, right? So now it's moving from the incidence matrix to the transition matrix. Okay, so then we can define a new reproduction number. Okay, so the R lot tiered. Okay, so the R lot tiered now is the sum of the reproduction numbers associated to the sexual transmission, mosquito-borne transmission, and the vertical transmission. So now for this R naught, it is easy to obtain the relative contribution of each transmission route, right, to the reproduction number. So we define a new R naught. Okay, so then we also study the relative contribution of each transmission route to the instantaneous host infections. So like if you have 100 host infections, right, so how many or what's the contribution of sexual transmission? What's the contribution of mosquito-borne transmission? Or what's the contribution of vertical transmission? So we want to know that. So then we find that we can calculate that, right? So this here we obtain the relative percentage of instantaneous host infections due to the three transmission route and the time t. So this is instantaneous the contribution of each transmission route to the instantaneous host infections. In particular, like when the disease became endemic, we consider like this instantaneous host infection as the unique endemic equilibrium. So then we obtained the PS, PM, and PV, and we find that as the endemic equilibrium, the contribution and the endemic equilibrium, the relative contribution of each transmission route to host infections and the reproduction number are almost the same. So they are almost the same. Like okay, so then we do some data fitting. But due to the lack of high quality Zika case data, we fit our model to the GBS surveillance data in the northeastern region of Brazil. So because there's a strong correlation between excess GBS case data and GBS cases and the Zika infections. And so here we fixed the parameters like D, C, theta, gamma, and mu H and mu V, or fit parameters A, beta, and rho. So rho is the ratio of reported excess GBS cases to Zika cases, Zika virus cases. Okay, so we obtained like you can see that the fitting looks good, right? So here the black dot is the reported cases, and the red curves are for the simulated curves. Okay, so then we use the fitted parameter values to perform local sensitivity analysis, and we also compute the PRCC, the partial correlation coefficient, and you can see that R naught is more sensitive to to A, right? To A and also to M, right? So that means R naught is more sensitive to parameters related to mosquito-borne transmission, right? The parameter, but not okay. Okay, so I mean that so R naught is more sensitive to parameter related to mosquito-borne transmission, and then those of the other two transmission routes. Right? So this means that reducing the mosquito bites, right? Mosquito bites and the vector population size is most important for successful Zika control program. Okay. And then we for giving parameter sense for this given parameter sense, we calculate the best reduction number. So now it's R naught tiered, and also the endemic equilibrium, and then we calculate the the relative contribution of each transmission route to the R0 and to the host infections. And you can see that these two values are very close, right? So the contribution, the percentage of contribution of each transmission route to the host infection and to the reproduction number are almost the same. So here you can see that the sexual transmission, like their contribution is about 5%, and the mosquito-borne transmission is about 94%, but the vertical transmission is only 0.3%. Right? So this is for the for in R0 and the endemic realm. But if we only consider the first epidemic curve, and at the very beginning, you have a completely susceptible host and vector populations, and if we introduce infected humans into the population, so then you have an outbreak, right? So this is the first epidemic curve. So that is approximately from day 0 to day 180. So then we calculate the cumulative number of host infections. So that is about if we have total population is 100,000. 100,000. So this is the cumulative number of host infections. So then you can see that then we can compute the percentage of contributions of each transmission route to the cumulative host infections. So that is about 9% contributed by sexual transmission, and 90% by mosquito-borne transmission, and 0.23 by vertical transmission. Right. So you can see that the role of sexual transmission is the only phase of Zika outbreak is greater than the long term, right? While the vertical transmission is just the opposite. Okay, so in this talk, I presented two models of for Zika transmission. One is an epidemic model with 2 transmission routes. The other is an endemic model with 3 transmission routes, and we evaluated the relative contribution of each transmission route to the basic reproduction number and the host infection, the host infections, and statistical analysis showing that reducing mosquito bites on the vector boundaries is most effective in controlling Zika virus disease. And of course, there are still much room for improvement, right? Because usually the mosquito population, the size is time varying, right? So it's important to consider seasonality for mosquito population. And also it's important to consider incubation period in mosquitoes, because mosquitoes only have a short a lifespan. And if they have a long incubation period, they probably, the infected mosquitoes probably die before they can transmit the virus. Right? So, okay, so here are my collaborators, and Xiao Yan is a second-year master student in my group, and my talk is based on these 2 papers. So if you have interest, you can ask me for a copy. Okay, so thank you so much for your attention.
Thank you very much for this very nice talk. Very interesting. It's time for question. So I have some question, but I want to let the other people start. So please, if you have a question, please raise your hand or just use the microphone, right? So any questions so far? Andrea demandait. Non. Voilà. Here, maybe.
Can I ask a question?
Sure.
It was a very interesting talk, and Nora, I missed one thing. Perhaps I just arrived a few minutes late. I don't know if I missed a point. When you fit the data in Brazil and Colombia that have two peaks, you have some seasonality in the model. Where does it come from that you have the two peaks?
Yes, there are two peaks. Yeah. So in our fitting, we choosing. I think we assume that the mosquito population size is time varying. It's not a constant in our model. I think. Yeah, there's two epidemic curves.
Okay.
Yeah. So but there's so here we fit our model to the GBS data, not the Zika the reported Zika case data. And so in our paper, then like the editor asked a question like why not fit the data to the like the case of a microsymphonia. They ask a question about that because we fit the GBS data. So the editor asked us a question like why did you fit the data to the microsymphonia that data, because that data is not like does not have two waves, but the GBS data has two waves.
GBS means what? Means
the Guillain-Barré syndrome.
That's another disease then.
Yes, yeah, but that's disease is correlated to
Zika?
like Zika infections.
It's similar, you mean?
I mean, like Zika infection can cause the GBS.
Okay, yeah. I see. Okay, and then if I may, you talk about simulation here for the red curve, but it looks very irregular to me, right?
Yeah, the red curve.
Very irregular, right?
Yeah, irregular. Yeah.
So how do you get that? I mean, it's not coming from an OD model, right?
Yes, it's actually I'm not good at the fitting model. This part is was done by Dr. DaoZhou.
Who?
And DaoZhou from Hong Kong Polytechnic University.
I know. I see. but this, in fact,
it seems that he used the supply function to fit.
Yeah. Sure. So it's not really it's a regularization of the model of the data, right?
Yeah.
It's not really a simulation coming out from the OD model, right?
Yes. Yeah.
Right. Yeah. Okay. I see. It's a sort of regularization, and based on that, you can compute the R0 or something.
Yeah,
right?
Because you see the curve is not smooth.
Yeah, sure. It's very irregular. It's a big problem everywhere, right? Okay, sounds very interesting. Oh, so you are using for Zika GBS, which is another disease caused by Zika.
Yes,
Because basically, and so the data for GBS are much better than Zika, or what?
Yes, the data for GBS is much better because the GBS the symptoms are like it's easy to see, right? But for the Zika the symptoms like most or like only 20% of Zika infections are symptomatic, and the symptoms are usually like mild or symptomless, right? Or there's no symptoms.
Yeah. I see. Okay, I see. So can you go maybe another question? Andrea, do you have another question maybe? No.
No, that was my question.
Okay. Any more question then?
There's a question on the chat, I see.
Let's see.
Could you shed some light on the difference between the epidemic model and the endemic model?
Okay. Yeah. That's a good question. Yes. Yeah. So here I present presented two models. Right. The second in part 2 I presented epidemic model, and in part 3 I present endemic model. So let's go back to
Yeah.
okay, let's see. Let's go to the, so can you still see my screen?
Yeah, sure.
Okay, let's go faster.
Yeah.
So here you can see, so for this model, you can see, so here in this model, I do not consider the human death and the both, right? So there's no both and death. And then like this is like like we consider a simple SIR model. If there's no both and death, right, then you can consider final size problem, right? So then finally the epidemic will over, right? Will end there. So here we do not consider both and death for humans. So that means the disease cannot become like become endemic. So this is we call epidemic model. So there's an epidemic, right? Okay, so but for our second model, there's both and death. Let's go to model equation. So here we consider the death and the human death and both. Very simple. We consider like the both and death rates for humans are the same, but we still consider the death and both. So that means you have like new susceptible, so new susceptible humans. Like, so then the disease can become endemic in a region.
Maybe the distinction is about long-term, short-term modeling, because the distinction between these two types of model is you want to look at the short-term in the first case.
Yeah, that's right.
Long-term in the second case, right? Right.
Yes, yeah. If you only concept about like short-term,
because both models are
okay,
epidemic model. In fact, both models are epidemic models. They are modeling epidemics, right? So
yeah.
maybe a better distinction would be long-term, short-term modeling or something.
Yes.
Or,
yeah. If you want to study the long-term dynamics, so then you need to consider the wider dynamics of humans and mathematics.
Right.
Yeah. So they need to consider endemic models.
Yeah. Okay. So, any other question? Another one here. Please go ahead. Demandez. Here.
May I ask a question, please?
Sure.
Okay, thank you, Gal, for a nice talk. My question is just coming from model parameters. Model parameters, especially for those range. How did you come up with those range for model parameters?
Oh, so this parameter ranges from literatures. Yeah. So mostly from literature, from other papers. Yeah.
Okay, from other papers. Okay, fine. I thought maybe you come up maybe with fitting then.
If you have interest, you can take a look at the paper. In the paper I give some references.
Okay. Thank you.
Thank you.
About the parameter, may I ask another question? You show a figure with some bar on the right and the left side, right? Left-hand side. I did not quite understood this one.
Which one?
Can you go back to the page where you get the parameter, all the parameter with some bar? Parameter estimation with some bar or something?
Which
I forgot the page number, but in the second part for sure. Maybe close to that one. You see? This one. You got all the parameter, and I don't quite understand what's the meaning of those those bar here.
Oh, this bar is like from it's the sensitivity is like for the left part. So this part is we calculate the sensitivity index, So like that's So this value like is about like 0.9, right?
Uh-huh.
You can see the x-axis, right? From
Right.
-1 to 1, right? So this is
Right,
means
right.
the sensitivity index for this, like the R0 with respect to the biting rate is about 0.9.
But I don't understand what the meaning of the axis, the vertical axis, horizontal axis.
The different the horizontal. So this is the sensitivity index. So that is computed by like there's a formula. It's like the partial the partial derivative of R0 with respect to the parameter. And that times the parameter divided by R0. There's a formula. Yeah, yeah.
I thought this was really okay. I see.
Yeah. So that if this number is large, the sensitivity index is large. That means the R0 is very sensitive.
To that parameter. Oh,
Yeah.
I see. Okay. Thank you very much.
Thank you.
So okay. That's a matter of the sensitivity of R0 with respect to each parameter, right?
Yes, yeah.
Yeah, okay.
So the left, so this is I prefer to call it like a local sensitivity analysis, because you only work for like a given parameter set. But for this is the PRCC. This is for like you consider a parameter range. For each parameter, there's a parameter range. And then calculate the PRCC. That is somewhat like a global sensitivity analysis.
Right. Okay, sounds good. Okay, so if no more, are there any more questions, or should we thank the speaker here? Okay, so maybe we should stop here, and say I would like to thank you very much again for giving a presentation this afternoon in China, this morning in France. And thank you very much for this very nice and instructive presentation. Was very nice.
Thank you.
Thank you.
Thank you
So
for your
bye-bye,
organization.
everybody. See you next week. Bye-bye.
Bye-bye. Thank you.
Bye-bye.